Hello and welcome to StrathSEDS Critical Design Review for the Mach-23 launch competition. I'm Neve, I'm the team lead for StrathSEDS. If you have any questions about this design review, you can contact me at neve@strathseds.org. Without further ado, we'll get stuck in with Pablo, who's going to be going over launch vehicle design.
Hi, I'm Pablo and I'm our mechanical team lead, and I'm going to be going through our launch vehicle design. Concept hasn't changed massively since PDR. We're still looking at a single stage dual deployment rocket using a 75mm Cesaroni motor, which we'll get into. We use two Pyrodex ignitions using a piston to ensure that the payload is thoroughly ejected from the rocket, and through the wall fins to secure the fins thoroughly. And the electrical team will go into more detail on this, but we'll be using a Cat's Vega avionics for our COTS system controlling the deployment. So to look quickly at the changes since PDR, we've had to change our motor due to issues with procuring certain materials at Cesaroni. So that's gone from the L1115 to the L2375, which is a 75mm 4-grain White Thunder motor. We've added a camera to the nose cone in order to document the flight of the rocket for use in promoting society and social media and stuff. So for this, we've added cameras windows to the nose cone so that it can see outside. We've changed how the avionics bay works. Before, there wasn't anything there. And now that the electrical team have produced some beautiful PCBs for us, we have integrated those into how they're being mounted. The avionics, the boat tail used to be retained through axial screws, which were difficult to access all the way buried inside the boat tail. These were changed to radial screws that are screwed through the body tube, which should be much easier to assemble. An antenna bay was added aft of the avionics bay in the main chute bay. This is so that we can get the RF antennas away from all the steel threaded rods and stuff that could be causing interference or blocking RF signals. Hopefully we can get good telemetry that way. And finally, our fins have been changed from aerofoils to hexagonal profiles for their improved transonic performance. So looking at an overview of the rocket, you can see we go from the nose cone into the payload bay, then our avionics are in the middle, and then a main chute bay, and at the very back we have the motor zone. Looking in more detail at the nose cone, there are several parts made of fiberglass here, including the von Karman-shaped nose cone, the coupler tube, and the base of the nose cone, which has a steel U-bolt through it to connect the shock cord. The 360 camera, as you can see, is mounted on a 3D printed section. As I go through our presentation here, all 3D printed components are marked in this hideous shade of yellow, like the screen behind me, and the rest of the fiberglass things are marked in black. Looking further down from the nose cone, we can find the drogue chute, which will be deployed at apogee, the CANSAT, which will follow it out, and its parachute, and the ejection piston, which will also be made of fiberglass. The order of these is presented such that the drogue chute will be the first to be deployed. This means that we have the greatest likelihood of not going ballistic and getting something out for the recovery as soon as possible. Furthermore, with on the hopefully not happening the case that the ejection doesn't go fully to plan and only the drogue chute is deployed whilst the CANSAT remains inside the rocket, the force of the drogue chute's deployment has another opportunity to pull the CANSAT out of the rocket. Yeah. Moving on to the avionics bay, we can see that it has two bulkheads at either end, which are both made of fiberglass. The upper avionics bay is screwed into the threaded rods and is sort of fixed to move with the avionics bay. There's an O-ring around it to prevent leaks from the deployment charges above, and the bottom one is actually fixed into the rocket. Thus, the procedure for assembly is to slide the avionics bay in through the payload bay of the rocket, such that the threaded rods at the bottom align with holes that have been drilled in the rocket fixed bulkhead, and then it can simply be screwed in and fixed in that way. Here we can also see the SRAD avionics and GPS. and the CATS Vega and how they'll be mounted in the avionics bay, along with the respective 3S and 2S batteries, which will be using some power umbilicals that can be seen to receive power while on the launch pad. One of these connections is for a deployment pyrotechnic arming switch. So moving on to the motor zone, we can see here the motor is retained with a aluminium retention ring at the aft section. This is to handle the high possible heats in this area, which is further attached to the 3D printed boat tail, which will be acting as the mechanism through which this is retained. And you can see here the little white dots that represent the screws that will be retaining this radially, as was discussed. Moving forward, we see the hexagonal fiberglass fins mounted in the through-the-wall configuration to optimize their rigidity and strength during flight. Between the fins, we can see two of the 4 centering rings, which will also be made of fiberglass and epoxied in. This surrounds a fiberglass tube that will be housing the motor, and other things that can be seen here is the shock cord hardpoint for this section, and the aluminium rail buttons. And looking now in some detail at the fins and their dimensions, we can see that they're 200 millimeters tall with a tip-to-tip length of 303 millimeters. There's also a 25 millimeter tab that sticks into the rocket to allow them to be secured, as was previously discussed. These have a hexagonal shape with the edges being chamfered. Looking into flight safety, we're expected to reach a maximum Mach number of 1.25 with a velocity off the rod of 26.9 meters per second. This corresponds with a thrust-to-weight ratio of 18.25 and a peak acceleration of a hefty 240 meters per second squared. This kind of information shows to us that dealing with inertial loads is a key part of keeping our rocket safe. The static margin of the rocket in subsonic regime is 1.83, and at Mach 1.25 it rises to 2.18, which is well within what we would be expecting. Currently, motor procurement is being ordered from Cesaroni when rockets and things are ready. They've told me today or tomorrow when I call them, so we'll see how that goes. Looking now at the recovery subsystem, we'll be using 2 Pyrodex charges, as was mentioned earlier. The first will be deployed after 0.3 seconds of continuous negative vertical velocity. So this will trigger the first 1.7 gram charge, which will release the nose cone, the drogue parachute, and the CANSAT and its chute. After this, the CANSAT and the rocket will descend down, and upon reaching 300 meters, the rocket will deploy its main chute using the second 0.8 gram Pyrodex charge. Looking now at some flight simulations using 20 miles per hour of wind and a 24-inch drogue chute targeting a 30 meter per second descent rate and a 65-inch main targeting a 10 meter per second descent rate. By applying appropriate angles to the launch rail, we can ensure that our landings are hopefully within the appropriate distance from the launch pad. As you can see here, our apogees are predicted to be somewhat over 3 kilometers. We're happy to have some margin over the target altitude, especially since our peak altitude is highly drag dependent due to the high velocities of the rocket. So it can be quite easily changed by small things like rail buttons protruding from the surface.
So since PDR, we decided to change our COTS avionics board. This is due to procurement issues and also the fact that this is a brand new board that we're going to be using for our other competitions, which reduces the amount of complexity in development. This is the CATS Vega computer system. It's got its own ground station setup, its own integrated design for avionics. It's been tested for years in different competitions, and so we have high hopes for its capabilities and reliability. It's also working on a fully independent radio channel and independent power system that's to not interfere in the case of a failure. Our own avionics, equipped also with pyrotechnic channels, will be only performing on dummy fuses as to follow the Mach-23 regulations. You can see we're quite far into the design stage. We're almost finished with all of our schematic work, and we're nearing the end of finalizing the PCB design, which we'll be sending to manufacturing soon. We're obviously building on the very big set of experience we have from previous editions of Mach and other competitions. And this design is a culmination of a lot of our ideas. And the main feature here, as you can see, are waggle connectors for ease of wiring. We try to integrate everything as much as possible into a multi-board assembly to reduce the time for assembly and also reduce complexity in wiring. This also allows us for better control of the design itself. The main board, we're going for another year of reuse of design. Main board is going to be present in both the avionics, the payload, and on the ground station. It's also based on an STM32. There's no changes here. The particular component is locked in. We've already bought it. And also we're using USB-C as we mentioned in PDR. There's also a generic expansion header that we're going to be using for the ground station and for the payload itself. And this will allow us for future use and different scenarios, but in general provides a very nice way of connecting to different peripherals on the board itself. The top section is reserved for all the power systems, and that allows for nice separation for all those channels, the pyrotechnic channels, and for a better understanding of what's happening on the board. This year, we'll also mention that we're going for dual storage for redundancy. This is progressing very well. The particular components have also been chosen and locked in, and this allows us for safely recovering all the data that we're recording. In the case of a failure, if either one of them fails, the other one will pick up the slack. The specific GPS expansion you might have noticed at the top is to allow for a big grounding plane for the GPS antenna. This is to help with its performance and tracking. And this is going to be important because we are going to be trying to implement Kalman filtering this year to combine our sensors to get as much of an accurate position and orientation reading for both recovery and for our analysis later on. The sensors in question are an BNO 80085 and the latest from Bosch, the BMP 581, which should provide us with cutting-edge performance when it comes to altimeter measurements and orientation sensing. And as you can see, this is the top-level design of how everything is connected. This is how we're structuring the schematics as well. I'm not going to stay on here for too long. Now going over to the ground station setup. As I mentioned before, this is a fully independent COTS and SRAD system. The CATS Vega is operating at 2.4 gigahertz in the ISM band using the LoRa modulation. It's got its own ground station and own antennas. So basically everything there is separated, and it's going to be only obviously receiving from the rocket itself. On the 868 megahertz channel, we're going to be receiving from the payload and from our own avionics on the rocket for recovery. And here you can see the main board, the main computer is being used as a ground station as well, just connected to traditional Yagi antenna we've tried and tested last year. And this setup is just going to be powered off of a laptop that's going to be analyzing the data live and also sending it over to our live demonstration. The frequencies I mentioned are the 868 ISM band. This is all within regulations as far as power output goes. We can go up to 10% of a duty cycle at specific channels of that frequency, which will allow us for multiplexing of communication between the two sending boards, that's the payload and the avionics, as well as back communication in the case of sending commands before launch. The COTS radio has its own integrated antenna on the ground station itself, and also allows for external antennas to be connected. So we're pretty confident that this is gonna suit all of those needs. And as it's a tested design, it should have no problem connecting over a few kilometers.
All right. Real-time telemetry. Last year at Mach-22, we developed a dashboard that let us view the real-time telemetry. This year, we'll be revamping it with a new, modern, hopefully slicker JavaScript framework. Telemetry will be displayed in real time using the data transmitted to the ground station. Location information as well as visualizations of velocity and position will be displayed. This year, we'll also be adding the ability to simulate data using stored data packets. We'll use this to replay past flights or possibly show even more extensive data that's been recovered from the rocket. All our telemetry this year will be saved to dual redundant SD card and external flash on both the rocket and the payload, as well as all received packets being logged on the ground station.
Cloud-based telemetry. So this year we're thinking of doing something cool, which is going to be a mobile app, and we've decided to call it StrathSEDS SpaceLink. It is an Android and Apple app for our team or the public to view real-time in-flight data or to simulate past flight data. It is developed using Flutter, which is a Dart-based framework, to create and deploy to both platforms with one code base, which is simplifying it quite a bit. One code base is always nice. Data is streamed via the cloud using a real-time Firebase database, so they get real-time updates right to their mobile device from the rocket. That's pretty cool. They are subscribed to receive the latest flight data or to load past flights that we've done in the past, and that wouldn't be real time, but they can load it in and simulate it. This app will use the same design as the dashboard with the cool graphs, hopefully, and will fit as a compact view on mobile devices. So it won't be a HTML page, it'll just be React-based components used in Flutter.
Hi, I'm Barnaby, a member of the mechanical team here at StrathSEDS. I'm going to talk to you about the payload. Here we have a 3D model of the CAMSAT. It's 4.5 inches in diameter and has 4 legs, each with a solar panel attached to absorb energy from the sun for potentially mission extending purposes. It's made of fiberglass for the bulkheads on the top and bottom, and 3D printed for the rest of the structure, with four threaded rods holding up the top of the CAMSAT in this laddered configuration. In the leftmost image on this slide, you'll see 4 solenoids which hold the doors in their closed configuration throughout the flight until approximately 10 seconds before landing. In the middle slide, you'll see the 2 PCBs that are held in a diagonal angle within the CAMSAT such that they fit in the limited footprint. At the top of that image, you'll see the GPS board, which is held in an orientation which is optimal for the GPS fix. In the rightmost image, you'll see a central pin which holds springs for each of the 4 doors, and 2 battery boxes on either side to power the CAMSAT. Targeting an impact speed of 15 meters per second, we've calculated that there will be approximately 100 meters of drift at the optimal launch angle. This is assuming 9 meters per second of wind and about a 5-degree launch angle, which this was covered in earlier slides. For this descent rate, we need approximately 15-inch parachute.
Moving on to the ground station power, we'll be powering it with an NP7-12, which is a 12-volt, 7-amp-hour lead-acid battery. The 1-minute discharge is 48 amps, and it's got a capacity of 84 watt-hours. We haven't finalized a motor for the ground station yet, so I put in 2 options here. So there's one that draws 1 amp and one draws 1.7 amps. We're going to have 2 of them, so that's 2 or 3.4 amps. You can see that the total time this gives us is over 10 hours and over 6 hours. So either way, we'll have more than enough capacity. Now the electrical side of the payload board. We have our same main board as we do in the avionics bay, but now we've added the payload expansion board here. It's got 2 headers, and this is what we're feeding all of our solar panels into. So we've got 4 arms on the CAMSAT, Each arm has 2 solar panels. Each panel has 5.5 volts, 200 milliamps peak. So if we put 2 of those in series, we get 400 milliamps. And if we put all 4 arms in parallel, it gives us 22 volts at 400 milliamps. Now we're going to be measuring the voltage and the current coming out of this, and we're going to be feeding those into the batteries. So we can, the hope is to be able to go indefinitely off of this power. So the operation is going to look like this. The CANSAT is going to start in a flight mode. It's going to separate and come down. Once it lands, it will go into a recovery mode where it will use a different amount of power and it will control the solenoids and everything. And then after 4 hours, we're going to enter a deep sleep mode. What that entails is it will go into a much lower power draw mode where it's only measuring the sensors every so often. It will wait for the solar panels to charge up the battery, and then it'll be more active. Then it'll go into a standby mode after it discharges, and then it will keep doing that cycle indefinitely. Now moving on to the payload and SRAD avionics batteries. We're going to be using a 2S1P configuration of LiFePO4 cells, and this pack has an integrated BMS. These have a nominal voltage of 6.4 volts, a max continuous discharge of 5 amps, and a nominal continuous discharge of 1 amp. And it's got a capacity of 1.5 amp hours or 9.6 watt hours. We switched from lithium ion to LiFePO4 because it's got a much better safety factor. Now moving on to the power budget for the payload. There are a lot of things on here, but only a few of them actually matter. So I've condensed those into a better image, which is this. So we can see that the radio in transmit mode in flight is going to be by far taking the most power. Then it's going to be the MCU, then the GPS, and the rest. In the recovery mode, the solenoids are going to be drawing a lot of power, but that's only for a short time, and the buzzer is going to be drawing a lot of our power. And then in deep sleep mode, the MCU standby mode is going to be drawing the most current because overall we're drawing very, very little. So I'll move over to the SRAD avionics. Again, lots of numbers on here. But the most important ones here are the radio and transmit mode, the MCU and active mode, the pyro channels, the GPS. So again, flights at the top, and at the bottom, the buzzer is going to be taking the vast majority of power. So now we can look at how much time we're going to get. So our battery capacity is 9.6 watt hours. So I've converted our power draw in watts to hours. So you can see that avionics in flight mode is, we can power that for 14.3 hours. In recovery mode, we can power that for 22.7 hours. So plenty of time. Now the CANSAT is slightly more complicated. So for flight mode, we can last for 20 hours. Recovery mode, about 11.4. And in deep sleep mode, it can go for 63 hours. However, with the solar panels, hopefully that should be basically never ending. Now moving on to the electrical radio tests. We are going to be going up a local hill called Dumgoyne, and you can see for a very long distance. So we'll be testing our radio distance like that by just slowly getting further away and making sure we can stay in contact the whole time. We'll also be doing some shorter range tests before then, like from the other side of the room, that kind of thing. Moving on to the power distribution electrical tests. We are first going to be testing the regulator, making sure it can provide enough current and that the current limiting is going to be working well. We're going to test out the battery charging, make sure that the current regulating and constant voltage charging all stays within limits, and the umbilical charging. Basically, when we're connected, we want to be charging the battery up and pulling power from an umbilical. So we're going to make sure that when we disconnect and connect that, that's not going to cause any issues. Next is the pyro. That's less applicable for Mach-23. However, we're doing UROC after this, and so we are trying to get our pyro as reliable as possible. So we're going to be testing the short circuit, the high current draws, making sure the pyro interlock works as expected, and the pyro enable pins are working.
As is stated in the competition guidelines, all structural components must be able to take double the aerodynamic and inertial load without issue. We've calculated the overall loads for this to be 6,508 newtons of inertial load and 1,236 newtons of aerodynamic load. For more complex components, this will be modeled using ANSYS and the finite element method. However, in a few cases, we'll be using practical tests, such as loading the fins in longitudinal direction and the axial deflection of the fuselage and fins, which will be measured by marking deflection on a static reference surface. The ejection test that we plan to run will be conducted at a Scottish Aeronautics and Rocketry Association launch day. This is to check if there is enough pyrodex to properly eject the launch payload and the drogue chute with the nose cone, and also for the secondary event, which deploys the main chute. In testing, recovery will be done mostly through drop tests, either by dropping the CANSAT from a height to verify that the parachute deploys and works as intended, and from dropping it without a parachute from a given height such that it accelerates to its predicted ground hit velocity to verify its structural integrity. With that said, I'll be handing you over to our electrical team who'll talk a bit more about radio range testing. Okay, while we're talking about testing, I'd like to mention the CANSAT prototype that we made a couple of weeks ago. On the left, you can see the preliminary sort of version where we had just printed the 3D printed parts, and it's held together with string and biro pens. This was mostly just to verify the functionality of the hinges and make sure that all the clearances were as we had hoped. Then we moved on to using the actual aluminium axles and with the springs installed as they will be on the final CANSAT. This highlighted both the proper functioning of the mechanism in the way that we expected, which is excellent. However, it also highlighted a couple issues that we're happy to see now rather than at a later stage, in that the central column was too weak and experienced significant deformation, and that the springs we had originally planned need some more oomph to be able to perform a successful self-righting maneuver. And we're happy to have these learnings on board now, having developed this prototype, and we'll be taking them forward onto the final version.
So we've now reached a very important section of every design review, it's the safety section. Starting off with our risk assessment, which hasn't changed since PDR, but I've included the slide anyway. Things such as severe weather and travel problems have all been addressed here, and we have mitigations for all of these things. We've also looked at the Mach-23 guidance document to make sure that we're meeting all of the requirements, and we believe we are. Our motor is a solid commercial off-the-shelf motor with 4,905 Newton-seconds of impulse, cell class. Right now, with all of the calculations and stuff that we've done on our current design, our CANSAT is estimated to be around 1.6 kilograms, which is well over the 1 kilogram minimum requirement. Our primary mission is to use solar power to extend payload lifespan, as discussed earlier. And we have GPS and altitude sensors on board, both the off-the-shelf computers and our in-house developed computers. And again, these are both capable of storing and acquiring data. Our payload does not drift more than 1.5 kilometers from the launch site in any of our simulations. You can see this on our recovery simulation slide. And then our student-built avionics does not have control over any aspect of the flight, simply there for gathering data. Going on to the failure modes for both the launch vehicle and the CANSAT. I'm sure we've all seen risk priority number tables before, but this is the one that we're using, with the left-hand side being O for occurrence, which is how likely the event is to happen, 1 being incredibly likely, 5 being incredibly unlikely. And along the top, we've got 1 to 5 for severity, 1 being very not severe, 5 being very severe. So we'll start off with the payload. And we've got descent rate too high, which can obviously result in a lot of damage on landing in a light scenario, but can also result to severe injury to personnel or property in a more dangerous scenario. So we're decided to make sure that we've done a lot of ground-based testing, both the ejection and testing of the payload to make sure that the parachute's correctly sized. Similar problem is if the descent rate's too low and we end up drifting very, very far. I think we've learned from the last 2 years that having lots of drift on your payloads is not enjoyable, and we'd like to avoid that at all costs. So again, we want to make sure that we do a lot of testing and a lot of simulations to make sure that our parachute's properly sized and that the recovery system works as we expect it to. If the parachutes separate or tear or become tangled, obviously that will increase the descent rate, and we don't want that to happen. It will damage our payload, it could damage property. So this is a lot of making sure that everything is fastened correctly on the day, and also just lots of testing. We've definitely learned the benefit of testing over the last couple of years. In terms of on the electrical side, if the battery doesn't supply power, we're obviously going to be unable to communicate with the payload, which will make it a lot more difficult to recover. Then we'll have payload failure to won't be able to do any of our intended mission. So we're, again, lots of testing, ensuring the battery has adequate capacity, making sure that on the launch day we check the charge of the battery, making sure we have spare batteries that are charged, all that sort of thing. If there's communication failure, can't recover the payload, it will have a very hard time recovering the payload. So lots of communication testing before launch is going to be done. Equally with SD card write failure, we're going to struggle to get any data back if we can't write any data. So lots of software testing and checks. The data, as discussed by Kyle, is going to be saved to 2 different parts of the board. All data received by the ground station is going to be saved. And finally, if our self-writing mechanism does not function, failed part of our intended mission, which we don't want to happen. So as you can see, we've already started some testing on this, and we're going to keep going with that to make sure that it works as intended on the day. So moving on to launch vehicle recovery, some of this is a lot similar to the previous slide. Stuff like descent rate being too high, descent rate being too low, and the parachutes separating or failing to deploy can all result in damage to the vehicle and severe injury to anyone nearby and to any property nearby. So we plan to do at least 1 ground-based ejection test, hopefully more. We're going to be load testing the recovery system, lots of simulations, lots of ground-based testing before we actually launch the launch vehicle. In terms of the secondary deployment, we also need to make sure that this is fully tested on ground. This is both to make sure that the drill chute comes out as expected and to make sure that it actually separates into 2 pieces as we want it to. And finally for this, the launch vehicle design and construction. So if the center of gravity is in the wrong place, we're obviously going to have a very unstable and potentially dangerous flight. So we've made sure to leave room in the nose cone to add ballast so that if we need to shift the center of gravity, we can. If we have fin flutter or breakaway, again, unstable or dangerous flight. So we've made sure that we've selected stiff materials for the construction, and we're going to be load testing the fins. If the rail buttons are not attached securely, we're going to have a very out of control rocket off the launch rail. So we're going to be making sure that we attach the rail buttons correctly according to manufacturer specification. If the airframe bends or shears, again, unstable and dangerous flight, we're going to lose the launch vehicle and likely the payload as well. So again, strong materials for the airframe, make sure that we do lots of load and stress tests and that it is constructed properly according to best practices. If we have premature separation of the launch vehicle, again, unstable, dangerous flight. So we're going to make sure that we have properly sized and constructed centering rings that are then integrated into the structure properly. And as I mentioned before, ground-based ejection testing. So again, motor mount failure. We don't want the motor to be launched through the rocket on launch. We want the rocket to take off, obviously. This could result in serious damage to the launch vehicle and it would basically obliterate our payload. So again, making sure that the aft section of the rocket is constructed properly is really high priority right now. And then premature ignition of pyrotechnics on ground, loss of the launch vehicle, loss of the payload, injury, damage to property. They're all concerns for that. So again, make sure that we have ground-based testing of pyrotechnic safety systems and that our arming protocols are as they should be. So I'm now going to be passing you over to Matthew, who's going to be going into some of the budgeting arrangements that we have so far.
Onto the budgeting side of things now. We're very happy to announce a recently acquired sponsorship deal with JLC PCB. JLC PCB have agreed to give us a $140 coupon for any electrical components and manufacturing costs that we need from them. We're very excited to work with them on our electronics. Similar to PDR, we are still receiving £2,700 from the University of Strathclyde Alumni Fund. This was awarded in spring 2022. We still have £90 left over from the Mach-23 GoFundMe donators. Thanks very much to them. And the aforementioned $140 coupon, which brings us to £2,790 before any costs. Speaking of costs, some participation costs here. Our entry fees we've paid, that takes £600 from our alumni fund account. The next participation cost are the accommodation fees, which are £100 per person. These, we're planning on having our members cover this cost individually. If they want to stay in the accommodation, they can pay it compared to staying free for camping. We're not expecting any travel fees to get to Glasgow Central. Thankfully, it is about a mile to my left, so we should be good walking. As well as this, testing lab facilities. We've been offered to work alongside the University of Strathclyde electrical vehicle team in one of the labs in James Weir building. So it's unlikely that we will need to pay for any lab space. Deducting these £600 from the budget then leaves us with £2,190 plus the $140 coupon. We've put together an expected budget for each sub-teams. For mechanical, this is £1,500 roughly. For the electrical sub-team, this is about £1,180. And the keen mathematicians among you may realise that those numbers add up to a number greater than the budget which we currently have. We are about £500 over budget, but we're working on some measures to bring that cost down so that we are within budget and can afford this project. The first we're expecting is the body tube. This was originally going to be about £200 to buy and ship from America along with some other parts. However, these parts have now been replaced with a flat fiberglass sheet for things like bulkhead centering rings and fins, which we're getting. But the body tube itself, we've been made aware that there is a body tube currently in the university, which belongs to StrathSEDS, that we should very likely have access to very soon. This will be handy to save us like a very good chunk for our budget. Next thing, you go down to the next bold thing, is the 60-inch parachute that is planned for the Stratosphere 2's secondary main chute ejection descent. This is a very expensive component for something which is takes quite a bit of skill to manufacture, but doesn't take a lot of material. So we're looking into the feasibility of manufacturing our own parachutes using ripstop nylon, which will be considerably cheaper to buy over a pre-made parachute. Next up is the most expensive component, being the motor case and our reload. Right now, we don't have a solid price for these. We're running off an estimated price from other sources online. We're currently waiting for an invoice from the lovely people at Rockets and Things. After we have that, we can update the price. We can hope that it'll go down, but there's no certainty. So we've been looking into other ways of reducing it as well. That brings us next onto the other expensive components, our two pieces of avionics, the Cats Vega boards for the avionics and the Cats Vega ground station board. Each of these are quite expensive. However, due to we are planning on entering Europe. We're hoping that our application to Europe, which we've submitted, will be successful. Europe has announced that there will be a special offer for people entering the competition for these Cats Vega boards, and we're hoping that this brings the cost down as well. We're looking into other places to reduce costs, but we're making sure that we're not compromising on any safety measures in making things cheap. We've seen what happens when money is taken away from places that really need it, and launch success and safety can be jeopardized a wee bit. Thank you. I'll pass you back over to you.
So just to go over the changes that we've made to our project timeline, as you know, on projects like these, there's always delays. So we've had a bit of a delay with ordering our mechanical components, but we're getting there with that. And we've had to push back the design and all the subsequent tasks of our launch vehicle. This was just due to being a bit too ambitious with our timelines, I think. So we've learned from that, we've adjusted, we've given ourselves a bit more time to finish the final design and to build prototypes and test prototypes, but we're still well on track to be built, manufactured, tested by the time we arrive at Mach-23. Same with the CANSAT. I think we're a little bit ambitious. So we've had to push things back a little bit. But now that we know that most of our design's 3D printed, it's actually cut down quite a bit on manufacture time because we can leave things to print overnight, put them together in the day, and that shouldn't take too long. And again, although things have been pushed back, we did build in buffer time at the start of this project, knowing that there's always delays. So we still fit in the time frame that we want. The full Gantt chart, if you want to see it as a timeline, is attached to the slide. Sorry, it's just putting it onto the slide was a little too large. You couldn't really see the details, so I thought this would be a better way to do it. So thank you very much for listening to our critical design review. We look forward to hearing for your feedback. So just to summarize some of our major accomplishments since the preliminary design review is the build of our CANSAT prototype, which shows that our concept does work. So we're just going to keep developing that. Our CANSAT and launch vehicle are approaching their final frozen designs. There's just a few more tweaks that we need to make on both of those. And the electrical design, as you've seen, has made significant progress since the last time you heard from us. So next steps are just full steam ahead with testing and manufacture, especially of prototypes and also of the final build. And we look forward to letting you know how we've got on at our flight readiness review. If you have any questions, feel free to reach out to me, neve@strathseds.org, and I'll be happy to answer them. Thank you.